Calculus, Chapter 1, Section 2, Algebraic Limits and Continuity. Okay, look at the following graphs, and notice we have f of x equals x, g of x equals 3, and notice that f of x plus g of x gives us capital F of x. So for the third graph, we're actually adding together the first two functions. Okay? And as you're looking at them, I want you to, for all three graphs, just jot down the limit as x goes to 2 and the limit as x goes to -1, and do that for f of x, for g of x, and for capital F of x. Okay, pause the recording if you need to, and resume to check your answer. The solutions, that'll be on the next slide. Okay, here are the limits for each of them as x approaches 2. For f of x, we have 2. For g of x, 3. And for capital F of x, 5. And then as x approaches -1, for little f of x, we've got -1. For g of x, 3. And for capital F of x, 2. I want you to notice a few things about these. First of all, the limit of x as x goes to a is a. That would represent our function f of x. F of x was just y equals x. So whatever we were sending x to, that was the limit. All right, for g of x was just a constant. It was g of x equals 3. And for any x value, the limit is going to be 3 on that. So the limit as x goes to a number of a constant is just that constant. And then notice what we got for the capital F of x function. We discovered that the limit of x plus 3, which is what capital F of x was, it was the limit of function f plus the limit of function g. Okay, so those are a few things we can notice just from doing those simple graphs. Now, that leads us to some properties for limit properties. This is kind of setting it up. It says if the limit as x goes to a of f of x equals capital L, and the limit as x goes to a of g of x equals capital M, and c is any constant, then we have the following properties. First property, the limit of a constant is the constant. The limit as x goes to anything of a number is that number. Okay, limit rule number 2, the limit of a power is the power of that limit, and the limit of a root is the root of that limit. In other words, you can find the limit of the function first and then raise it to the power or take the root. In the case of the root, the limit has to be greater than or equal to 0 if n is an even root. Rule number 3, the limit of a sum or difference is the sum or difference of the limits. In other words, as we saw, if you're taking the limit of two functions, either added or subtracted, you can take the limit of each function and then add or subtract the solution. And rule 4 says the limit of a product is the product of the limits. So just like the sum, it works the same way for the product. So find the limit of each function and multiply those solutions together. Rule 5, the limit of a quotient is the quotient of the limits, assuming we do not have a zero denominator. And then finally, rule 6, the limit of a constant times a function is the constant times the limit of the function. And this is a combination of properties 1 and 4, but it's used frequently, so they're listing it as a separate property of itself, in and of itself. So example 1, we're going to use the limit properties to find the limit as x goes to 4 of x squared minus 3x plus 7. Pause the recording, give this a try, and then resume the recording to check your answer. Okay, we know that the limit as x goes to 4 of x is 4. And the limit as x goes to 4 of x squared is the limit as x goes to 4 of x times the limit as x goes to 4 of x, which is 4 times 4 is 16. And then we know that the limit as x goes to 4 of -3x is -3 times the limit as x goes to 4, which is -3 times 4, which is 12, -12. And we know that the limit as x goes to 4 of 7 is 7. So putting all of these together, we get 16 minus 12 plus 7, which is 11. Okay, so we have a theorem here. It says for any rational function of f with a in the domain of f, the limit as x goes to a of f of x equals f of a. In other words, if the number that you are using, that you are approaching with x, if that is a number that is actually in the domain of the function, then all you need to do to find the limit is put that number in place of x and solve. So try that with this example here. Pause the recording, give it a try, and resume to check your answer. Okay, so according to that theorem, all we need to do is, since the domain for this function is all real numbers because it's a polynomial, all we need to do is put 2 in for all the x values, and we do that, and we get negative 27. All right, now try this example. Pause the recording, give it a try, and resume to check your answer. Okay, again, 0 is in the domain of this function, so all we need to do is we need to substitute 0 in place of x, and we get the square root of 2 for our limit. Okay, now try this one. Pause the recording, give it a try, and resume to check your answer. Okay, this one was a little tricky. Negative 3 is not in the domain, so we cannot solve it using that theorem. We can't just substitute because it gives us an undefined answer. So, but what we can do is we can actually factor the top and we can simplify it, we can cancel, and then we can substitute. So if we do that, x squared minus 9 becomes x plus 3 times x minus 3. The x plus 3's will cancel and leave us with x minus 3, and now we can substitute and get negative 6. And if you look at the graph, you'll notice that there is a hole in that graph, and it is at the point negative 3, negative 6. The last problem demonstrated how we can algebraically find a limit for a value of x that's not in the domain of the function. Now these are cases where the limit may exist, but where the function itself does not. We can use this idea to expand our definition of continuity. The simple definition of a continuous function is that it's a function that can be drawn without lifting your pencil from the paper. But now we're going to refine that definition using the concept of limits. So here's our definition of continuity. A function f is continuous at x equals a if f of a exists. So there has to actually be something there. The limit as x approaches a of f of x exists. And the limit as x approaches a of f of x equals f of a. So 3 things have to happen here. The function has to actually exist at that point. So f of a has to have a y value. The limit also has to exist at that point. And the function, what the function equals and what the limit equals must be the same thing. And if they are, then the function is continuous at that point. All right, so let's try example 4. Tell whether this function is continuous at x equals 3 and why or why not. Pause the recording, give this a try, and resume to check your answer. Okay, so first of all, we make sure there is actually a value for f of 3, and there is, it's 4. And then we use our theorem on limits, and we find that the limit is 4. And since the limit and the function are equal at that point, then the function is continuous at x equals 3. Okay, now try this. Is it continuous at x equals negative 2? And a piecewise function can be continuous, by the way. So your job is to discover if this is continuous and why or why not. Pause the recording, give this a try, and resume to check your answer. Okay, first of all, there is a function value at negative 2. G of negative 2 means we're going to use the x minus 1 because that says x minus 1 when x is greater than or equal to negative 2. So we'll do negative 2 minus 1 and we get negative 3. Now we need to see if the limit's the same. So what we need to do for that is we need to look at the left and right hand limits. Now we already actually know the right hand, and that's what we just got, which is negative 3. But we also need to put negative 2 into the other equation, the 1/2 x plus 3, and see if we get the same thing. So we do. We put negative 2 in and we get 2. So the limit as we approach negative 2 from the right is negative 3, but the limit as we approach from the left is 2, so they're not the same. The limit does not exist, therefore it is not continuous at -2. All right, this is just a summary of what we talked about. So read through these, pause the recording to give yourself time. There's a little bit more on the next slide, and then we'll do some additional examples. Okay, as you go through these practice problems, pause the recording to give yourself time to try them. Resume to check your answers and continue doing this till the end of the recording.